Here's another example of using Newton's method to calculate zeros. We're going to do this a little differently. You could probably tell from the last example that it's pretty repetitive. So set up this chart here to take care of some of that repetitiveness. And you can try this if it helps. We're going to approximate the zeros of this function. And we're going to continue the iterations until two successive approximations differ by less than 0.0001. So by iterations, that just means the number of times you did it. So I've already calculated f of -2 for this function to be -9 and f of -1 to be 1. So by the intermediate value theorem, the zero has to occur between -2 and -1. So my first guess, which is going to be my first iteration, is going to be, let's just split the difference and go -1.5. That's just a guess. I would say maybe since 1 is closer than 0 than -9, maybe -1.2 would be a better guess. But we'll go with -1.5 because these tend to get pretty close pretty quickly. So here we go. I graphed the function and its derivative to make these two next calculations easier. Here's the graphs. Now second calc value, and the value at -1.5, enter. Look up here to the upper left, make sure you're on the right graph. That's the regular graph. I'm getting -2. I'm going to put the zeros in. I just want to make a point. If we're trying to get accurate to 4 decimal places, all these answers better have 5. So you don't have to break the zeros, but if it does have decimal points, you should. Now I'm just going to cursor up, and that will give the value of my derivative at -1.5, and that's 9.5. So now you just do the calculations. Calculations are at 9.5. Oops. -2 divided by 9.5. That's that number. Normally I would put it in here, but I'm just going to keep going because I'm really interested in the final. The next thing I'm going to go x sub n, which is -1.5, minus the answer I just got here. So -1.5 minus this. And I got -1.2 8947. So that was 5 decimal places. And now I just continue from there. So and now my second iteration is going to start with that new intercept. So on the calculator, calculate the value. At -1.28947, -33589, do the same thing with the derivative. So cursor up, 6.3 3974 39746. So now I'm going to take the negative 0.33589 divided by the 6.39746. That's the column that I'm not writing in. And then take this number and subtract this result from that number. So negative 1.28947 minus this to get my result of negative 1.2413. One more decimal place. 413131. And here we go again. So my third iteration, start with negative 1.24131. Value is negative 1.241. Right here. Yeah. Derivative. Now I'm going to calculate x of n, negative 1.24131 minus negative 0.0431858 over 5.76248, and I get this number. And now I'm going to stop when I'm going to stop right now, but I'm really not done. I'm going to stop when this number, I screwed this up. This number here and this number are off by 0.0001. They're getting closer, and they're going to start to get closer a lot quicker. The answer to this question is, well, it's going to be negative 1.2337-ish, I believe. And the last thing I want to do is quickly check what the calculator shows the 0 to be. So I'm going to second calc 0. Make sure it's talking about the first function, which it is. Left bound is negative 3. Right bound, I'm going to go 0. Enter for the guess. The actual 0 is negative 1.23375. So we were starting to get very, very close. It may have taken only one more or two more iterations. So that's it. The table is a nice organized way to do this. The only time you get any of these problems wrong is if you just like miswrite something, miscopy something, which happens a lot. And one last thing I want to warn you about is make sure you read the whole number, because sometimes the number gets very, very small. It might say like 0.2355 e negative 4. So make sure you understand that really means 0.000, etc. So that's it.